Ok, pessoal, todo mundo pronto? All right, so I think we should go back to business because, well, 4 minutes after the time. Okay. This slide here is for you to look at and think in terms of what, based on what we have spoken before, what do you think that the ocean circulation driven by the wind would look like? As I said, because of the balance of forces, and mainly because of the Coriolis effect, the ocean at the current at the ocean surface is not necessarily in the direction of the wind. It's kind of to the right in the northern hemisphere and to the left in the southern hemisphere. In the absence of continents, in the end the circulation will be predominantly from east to west or from west to east, depending on the latitude. But we have continents, and because of the continents, the circulation looks like we see in this picture. And that's because of this effect of the wind blowing in one direction and the circulation at the ocean surface to be more or less diverted to the right or to the left, depending on the hemisphere. In the end, you have the predominance of these gyres, or gyre, or circulation in form of closed gyres. And the direction of the flow is either clockwise or counterclockwise. In the northern hemisphere, as you can see in this or in this picture, in the two basins in the northern hemisphere are clockwise. As you can see, the circulation in the Pacific is from north to south along the United States western coast, and then from east to west, and then from south to north, and from east to west. And this is what we call anticyclonic circulation. Anticyclonic circulation is a circulation in the clockwise sense in the northern hemisphere. Remember it. Anticyclonic is clockwise in the northern hemisphere. So you have an anticyclonic circulation in the northern Pacific, also in the northern Atlantic. On the other hand, in the southern hemisphere, you have circulation counterclockwise, and we call it, again, anticyclonic. So I know that this is kind of confusing, and when I started learning this, I said, well, wait a minute. I have to create a way to memorize. I am from the southern hemisphere, and we, in the southern hemisphere, we are right. We are correct. We are on the right side. So what is anticyclonic is anti-clockwise. There is not this one way and the other. So what is counterclockwise in the southern hemisphere is anticyclonic. In the northern hemisphere, you guys from the northern hemisphere, you are wrong. You do it in a different way. So what is anticyclonic for the northern hemisphere is clockwise, or what is cyclonic is counterclockwise. Did you get it? Yes. All right. So for me, it helped maybe it helps for you. So if you want, they ask you a question. What does anticyclonic mean? You can say, well, you take 2 minutes thinking, so well, I'm from Brazil, in Brazil we are right, and what is counterclockwise is anticyclonic. So anticyclonic is a counterclockwise circulation. Or if they ask, what is cyclonic? It's a clockwise circulation. In the northern hemisphere is the opposite. Because the northern hemisphere is the opposite to us. And for them, it's the opposite. So you don't have to pay for this. It's already paid off. So the ocean circulation driven by the wind is predominantly represented by gyres that are anticyclonic in the subtropical regions of the northern hemisphere, and they are cyclonic in the polar regions. See, there are people on the other side, but it's more difficult for me. But in any case, if you see, this is what we call the subpolar gyre in the Pacific. It's a cyclonic circulation. The same happens here. Do you remember that circulation pattern that the Vikings took advantage of to get to the Americas? They left from Scandinavia and came to the west and then returned from west to east in this kind of cyclonic circulation or counterclockwise circulation. In the southern hemisphere, we don't have circumpolar gyres because we have only one current that goes from west to east all around Antarctica, and this is named the Antarctic Circumpolar Current. The Antarctic Circumpolar Current is a current that goes from west to east all around Antarctica. And the South Atlantic or the South Pacific, we have anticyclonic subtropical gyre. In the South Atlantic, the same thing, and in the Indian Ocean, the same thing. There are some gyres in the tropical region that are less important, so don't worry about that at the moment, or at least in this course. So, in general, the most important features for the ocean wind-driven circulation are the subtropical gyres, the circulation that can be represented more or less like what you can see. There are two subtropical gyres in the northern hemisphere, the North Pacific and the North Atlantic, and three subtropical gyres in the in the southern hemisphere. That is in the South Pacific, in the South Atlantic, and in the Indian Ocean. But in reality, things are a little bit different. And this is a computer simulation of the circulation in the Indian Ocean and the South Atlantic. And the colors represent the sea level height above average. So if the ocean if the ocean were in rest, it would have a surface distribution. Because it's moving, there are regions that are above average, others are below average. And the red means above, and the bluish colors mean below. So there are these differences. And if you look at the Atlantic, the South Atlantic, you can see that near the Brazilian coast, near South America, the colors are reddish, are more to the red. And on the other hand, near Africa, the colors are bluish, meaning the ocean surface is higher near the South American coast than near the African coast. Why is that? Why is that there is this kind of intensification or the more energy near the western boundaries of the ocean? Well, I will give you the answer, but in any case, remember this. The circulation of the ocean near the surface, or the surface circulation of the ocean that are mainly driven by the wind, they have this sort of westward intensification or western intensification or west intensification. That is, the energy is concentrated more to the western side of the basin. And the explanation is simple. It's because the Earth is a sphere that is rotating. Because of the rotation and the sphericity of the Earth, the Coriolis parameter exists, or the Coriolis effect exists, and the Coriolis effect varies with latitude. And the variation of the Coriolis effect with latitude is what causes this west intensification. Of course, we don't have time here to explain in details the dynamics and the balance of forces. But imagine that I am a priest preaching, saying something, and you always believe in a preach without asking questions. So do the same. Believe me. The ocean circulation is intensified in the western parts of the basins, and this intensification is due to the sphericity and rotation of the planet. This does not exist in a flat Earth. And this can be seen in all ocean basins. There was a question, a girl came to me and asked, well, tell a little bit more about ocean basin, because this is in the title of the course. Well, ocean basins, what we call, are the geographical regions where, for some reason, we define as, for instance, the Pacific Ocean is a basin. The Atlantic Ocean is another basin, and the Indian Ocean is another major basin. So on Earth, we can define three major basins: the Pacific, the Atlantic, and the Indian Ocean. And each of these three are subdivided in regional basins. So we have the North Pacific, the North Atlantic, and the South Pacific, South Atlantic, and the Southern Indian Ocean. The Northern Indian Ocean is kind of limited. There is not much of a, but there are some. But there are even smaller regions. For instance, we can call the Arab Basin or the Arab Gulf Basin. So you can go to smaller regions and call them a local basin. So basin is a name used to represent certain region of the ocean. There are the major basins and regional basins. And in this slide, what you can see is the global circulation in a flat Earth. Again, so I'm kind of because, you know, in order to represent the planet in a way that you can see the entire surface, you cannot show a sphere, because in a sphere you only see a side of it. So in order to see everything, you make it a plane. And of course you can learn with that. But that, please, don't think that I'm an advocate of the flat Earth. This is just to show that you have three major basins: the Indian Ocean, the Atlantic, and the Pacific. And the Pacific, of course, is the larger one. And in all three, you can see that the colors are more to the red on the western side of the basin. When I say the western part of the basin, I'm looking at the ocean and looking to the west or to the east of the basin. Of course, the western side of the basin is the eastern part of a continental region. So but we're not talking about continents, we're talking about the ocean. So when I say west or east, I'm talking about the western side of the basin or the eastern part of the basin. And the ocean in all basins is more energetic on the western side, and this is because of the sphericity and rotation of Earth. But in this slide, I also would like to call your attention to the fact that in the polar regions, you have a different distribution than in the subtropical regions. And this is mainly because of the different insolation, and I'll talk about this in the next slide. More specifically, how many of you are from the Pacific region, please? Okay, there are some. How many of you are from any Atlantic region? So that's why I'm only showing details of them. This is bias, right? Yeah. No, because I am from Brazil, and of course, my main subject of study is the Atlantic, and also because, like it or not, the dominance of the old world politics are still the North Atlantic. So we know much more about the North Atlantic than any other ocean basin. And that's not true for the South Atlantic. We know very little about the South Atlantic. But in any case, if you look at this picture, and if you think about the Pacific, it's not going to be much different. You have a subpolar gyre in the Atlantic, you have also in the Pacific. You have a subtropical gyre in the North Atlantic, you have the same in the Pacific. You have an Atlantic equatorial gyre, and you have the same in the Pacific. And you have the Southern Hemisphere subtropical gyre in the Atlantic, and also in the Pacific, and also in the Indian Ocean. And you have the circumpolar current that is all around the pole. So it doesn't make a big difference showing the Atlantic or the Pacific in terms of the general distribution of surface currents. But let's go back to the thermodynamics. We know that the ocean is circulating. We know that the planet is receiving much more heat in the tropical band and is losing heat in the subpolar regions. And somehow, this excess of heat from the subpolar, subtropical regions must be exported to the higher latitudes. And if you look at this colored figure in this slide, you can see some round arrows showing the sense of the circulation. In this picture, the red means warmer, and the bluish color means cooler. And it's clear that from the tropical regions in the Pacific or in the Atlantic, there are waters going north, carrying heat, and returning to the south, bringing cooler waters. So heat goes north, and cooler water comes south. Gets warmer, goes north. Gets cooler, goes back. And this is a thermal machine. This is a way Earth is using to bring heat where heat is in excess to regions where heat is in deficit. And what happens in this process is that in those higher latitudes in the Atlantic or in Indian Ocean, in the Atlantic or in the Pacific, or in the three basins in the Southern Hemisphere, you have the ocean constantly bringing heat from the tropical regions to the mid-latitudes, and in the mid-latitudes, the wind gets heat from the ocean cools the ocean, and the ocean brings the cooler water back to the south. And what happens to the heat that the atmosphere takes from the ocean? Well, through this atmospheric turbulence, through the storms that happens or normally around what they call the storm track, that all the way the westerlies circulates both in the northern and southern hemisphere, redistributes the heat to the atmosphere and to the rest of the ocean. I'm going to talk a little bit more specifically about this in the North Atlantic in following transparencies. Well, there's another important component of the ocean movement, is the vertical motion. We are talking about the ocean circulation driven by the wind. This is normally wind blowing and moving horizontally the water. But the water also moves vertically. And the vertical motion is mainly due to convection. In a region where water gets cooler, it gets heavier and sinks. Where the water gets warmer, it gets lighter and rises. And this generates some sort of convection cell. More or less similar, actually, to what happens to the atmosphere. And this is a very important component of the climate machine. This planet, we, human beings, we exist ultimately due to this process that is happening in the ocean. I'm going to tell you more about this and why I'm saying such a strong statement. Well, remember that near the poles, water gets cooler and sink, and near the equator, water usually gets lighter and rises, so you have this kind of circulation pattern. And what is the importance of this to the climate system, to the environment as in general? Well, there is this, do you remember that movie that I showed at the beginning? There was this global thermohaline circulation. This is a beautiful name, something that sometimes you see people talking about, but most of people don't understand exactly what this means. The thermohaline circulation. To begin with, the term thermohaline means something that is due to temperature and salinity. Thermohaline circulation is a circulation that is driven by gradients of temperature and salinity in the ocean. And this is a global system that can be summarized by this figure that you see, and I'm going to show a little movie about that. What you see in this picture is that in these two regions, the North Atlantic and the Antarctica region, this Weddell Sea, there are two regions where water gets very heavy and sink. The sinking of water in these two regions are in the measure of 40 sverdrup. 40 sverdrup, 40 sverdrups. What is a sverdrup? Sverdrup is a unit that we oceanographers invented to represent 1 million cubic meter per second. Okay. 1 sverdrup means 1 million cubic meter per second. So in these two regions, each one of them is 20 million cubic meter of water is sinking. 20 million cubic meter of water is sinking at each second. 1 second. 20 million, another second more. So it's a huge amount of water that is sinking. at every second. And the question is, well, what is sinking? So the surface of the ocean is going to be depleted of water. A big hole is going to appear at the surface of the ocean because the water is sinking. Is that true? No, because the water that sinks, of course, would create a region with less water. But nature hates vacuum. If there is a vacuum, nature finds a way to fill it immediately. So water from other regions come and fills the vacuum, and then water that came from somewhere will be replaced by water that came from somewhere else. So you generate a circulation pattern. So to shorten things, water that sinks in the North Atlantic goes south. You see this blue line. The blue line means water that are sinking in the Norwegian Sea, goes to the south, joins to the circumpolar current, and then part of it enters the Indian Ocean near the bottom, and then gradually it goes back to the surface. Gradually it upwells. Another part continues enter to the Pacific and gradually comes back to the surface. And then from the Pacific it goes to the Indian Ocean through the Indonesian Straits, joined to surface water in the Indian Ocean, and goes to the Atlantic by the southern tip of Africa, and then goes north, and then sinks again. So this is like a conveyor belt in a factory, or it's like that belt that carries the luggage in an airport. You have all those who ever flew and lost a luggage in an airport knows what means this conveyor belt. The luggage should come from one place and you take it, but sometimes it doesn't. But this is a very simple, very kind of naive stuff, but has a very strong meaning. I'm going to show a little move. Again, I ask people to turn off the light and close your fingers.
The global conveyor belt is the major system that carries heat.
Okay, let's go back to the beginning. Okay, this is going to be a representation. It's an artistic representation of the conveyor belt. I'm going to show it a couple of times. It's short, and then I explain, and then show it again. And I hope you end up understanding what it's meaning.
Global conveyor belt is the major system that carries heat in Earth's ocean. The heat transport of the system helps to moderate Earth's climate. This model shows in a simple way how heat is transported from the low and mid latitudes to the far North Atlantic. Shallow currents are warm and shown as red. Deep cold currents are colored blue. The moving pulse shows the general direction in which ocean currents flow. Cold, deep currents travel east past Africa. Some part of the flow rises in the Indian Ocean. The rest of the cold current continues flowing toward the North Pacific Ocean. In the Pacific, the current becomes warmer and less salty and migrates as a surface current toward the North Atlantic. In the North Atlantic, dry winter air cools the ocean surface. This removes heat from ocean waters and makes them salty and dense. When this water sinks to great depth, the global conveyor belt again begins its worldwide circuit. The entire process takes as long as 1,000 years to complete.
Thing missing here, because every time I see a movie, I speak Portuguese. Okay, please, leave the lights off. I'm going to show it again because this is important, and I think that if you don't learn anything else in this discipline, at least you're going to remember that this Thermohaline Circulation stuff, and it pays off, because this is really important. As you saw, the conveyor belt is a kind of a machine that is bringing heat from one place to the other, and then the water gets cooler and sink and sinks, and then it goes to other places and goes up and then goes back to the north, and then this is a kind of a continuum kind of a machine. And I'm going to show it again, and then I'll continue because there are some important aspects to be learned.
The global conveyor belt is the major system that carries heat in Earth's ocean. The heat transport of this system helps to moderate Earth's climate. This model shows in a simple way how heat is transported from the low and mid latitudes to the far North Atlantic. Shallow currents are warm and shown as red. Deep cold currents are colored blue. The moving pulse shows the general direction in which ocean currents flow. Cold, deep currents travel east past Africa. Some part of the flow rises in the Indian Ocean. The rest of the cold current continues flowing toward the North Pacific Ocean. In the Pacific, the current becomes warmer and less salty and migrates as a surface current toward the North Atlantic. In the North Atlantic, dry winter air cools the ocean surface. This removes heat from ocean waters and makes them salty and dense. When this water sinks to great depth, the global conveyor belt again begins its worldwide circuit. The entire process takes as long as 1,000 years to complete.
Well, you heard in the end that this entire process can take as long as 1,000 years to complete. So it's a very slow kind of movement. It's not something that happens in 1 week or 2 weeks or 1 month, 1 year. But even so, it's important because it is a climate-related process. It's not weather. It's not it's going to rain or it's not going to rain today or tomorrow. It's something related to what is going to happen in, let's say, 100 years, 200 years from now, or even longer. This is one point. And another aspect is that how is this sensible to what's happening to the climate? So does the climate change affect this? And if it affects, what would be the feedback? What would be the response from the ocean to the climate system? And this is what we're going to try to understand in the next slide. Well, to begin with, if you look at the Atlantic Ocean in terms of the vertical distribution of temperature or salinity, in this case I think it's salinity, and this is what you see. You have waters that are going from south to north in the upper part of the ocean, and then you have a return flow in the deeper regions of the ocean. And also you have a saltier water going north and returning as cooler water. This is something that is there, and the question is, how important is this kind of overturning circulation? We call it overturning because you have water going this way and returning. And what is the fragility of this system, and what would be the consequences of changing this circulation pattern? Again, look at the circulation, namely the circulation, the conveyor belt. This is what we see today, or when I say we don't see this. Actually, no one can see this sort of, because this is an average, this is a kind of a very crude representation considering a long-term average. In general, in average, the mean pattern of circulation is this: water going from the Atlantic, South Atlantic to the North Atlantic near the surface, carrying warmer water, releasing the heat to the atmosphere in the North Atlantic, sinking and coming back, and then eventually returning. And this is what you would expect if you were patient enough to stay, let's say, 5,000 years observing the ocean and taking notes, and then in the end you make an average, and this is what you would get. But if you go back to past, let's say if you go 20,000 years in the past, for instance, how can you do that? Well, there is a branch in oceanography that is the geological and the paleoclimate experts, that they try to understand what happened in the past, collecting proxies or collecting some sort of indicators of the environmental conditions in different times. And one way of doing that is collecting cores. When, they go to the ocean and somehow collect a tube of the sediments in the bottom of the ocean with 1 meter, 2 meters, 10 meters length. And in some way they preserve it and dry it, and then they start studying using the following technique. They consider that at the surface of the bottom is the present. The bottom would be sometime in the past. And in between, of course, the different ages. And they say, well, somehow they find that 1 centimeter means 10,000 years, depending on the sedimentation rate. So there are ways of evaluating that. So you can say, oh, this core or this tube of sediment has 10,000 or 20,000 or 200 million years, whatever. And then they take one part of it and say, this corresponds to, let's say, 20,000 years in the past. So you understand this? Okay. There were some scientists that went to near Africa on the Atlantic side and took some sediment and started looking at the composition of the sediments. And they found that there's a bug that is you don't find this bug in the Atlantic, but you find it in the Indian Ocean. And in the sediment, you would find the bug because the water coming from the Indian Ocean normally brings this bug from the Indian Ocean to the Atlantic, and they die and goes down and remains in the sediment. So normally you find this, and then some time, wait a minute, it disappeared. There was a moment in the past that these bugs, they call it foraminifera, from the Indian Ocean, didn't arrive in the Atlantic. They stayed for a long period, and then they start getting back. So during this moment, there was no foraminifera coming from the Indian Ocean to the Atlantic. And now let's think in terms of an oceanographer. A geologist would say, well, we saw that in the sediments there were some foraminifera that are not from this part of the ocean, and then again they are, but in this period there was none. But the oceanographer, well, wait a minute, well, why is that? Well, the only way the foraminifera can come from the Indian Ocean to the Atlantic is being brought by the currents, because they don't swim. They are not good in swimming. So they don't do it by themselves. They were brought by the ocean circulation. If in a certain period of time they disappeared, that means that the ocean circulation was not bringing them. Either they died in the Indian Ocean or the ocean circulation was stopped in that period. And that was, in the end, this is a paper published in Nature, the magazine Nature, 4 years ago. So 5 years ago. So it's a reliable source of information. So these guys, to publish a paper in Nature, you know, it's not easy. I myself never had a paper published in Nature. Lucky those who had. But the conclusion was, about 2,000 years ago, the connection between the Indian Ocean and the Atlantic Ocean, what we call the Agulhas leakage. The Agulhas leakage is because there is a current in the Indian Ocean that named the Agulhas current. The Portuguese way of speaking, Agulhas. The English pronounce it Agulhas. But it's a Portuguese name, so I pronounce it the way the Portuguese used it. The Agulhas current is a current that comes along Africa, and then near the southern tip of Africa, it retroflects and goes back to the Indian Ocean. But sometimes a big blob of water from the Indian Ocean escapes from the Agulhas current as a ring and goes into the South Atlantic. And imagine this water full of foraminifera, of course, arrives in the Atlantic, and the foraminifera, they die there and they sink. And if you interrupt this connection, you don't bring more this bug to the Atlantic. And that's what they found. They found that 2,000 years ago, there was an interruption of the Agulhas leakage, and for that reason, the Thermohaline circulation was weakened, almost disappeared. And what happened 2,000 years ago, 20,000 years ago? An ice age. So they don't say who was born first, the egg or the chicken. They said, well, there was a weakening of the Thermohaline circulation at the same time that there was an ice age in the north or on Earth. So there is a correlation. You cannot say by this study who was the first, who caused what. But it's an indication that if you have a weakening of the Thermohaline circulation, the possibility of it happening together with a cool temperature on the northern hemisphere, it's very likely. And the question is, well, can this happen again? If so, why? Oh, this is something that is several people, several institutions or groups are trying to understand at the moment. And in order to understand this, I'm going to show you again another movie. I'm going to show two, actually. The first one is what is happening in the North Atlantic. This is what we call the North Atlantic heat pump. I'm going to say a few words first, and then I'll show you this animation, and then another animation, and then we close the reasoning. Well, what is the North Atlantic heat pump? The North Atlantic heat pump is water coming from south, full of heat and salt, reaches the higher latitudes in the North Atlantic, where the wind blows from America towards Europe. The wind leaves America very cool, gets heat in the Atlantic, and arrives in Europe with a much higher temperature. So this is a machine that is taking heat from the ocean and bring it to the Europeans. The Europeans could pay a fee for that. But that's true. So the ocean is providing heat to warm up the atmosphere that ends warming up Europe. This is what's happening day by day. And this is what I'm going to show you in this first animation. Again, please, can the lights be turned off? Thank you. Okay, there is no sound, so I would say, you see the red arrows in the ocean are heat coming from south, the wind coming from America is starting blue and getting head red, so warmer, and going to Europe. And the water sinks and flows back to the southern hemisphere. So what you see, I'm going to show it again. What you see is water coming from south, near the surface, warmer, the wind blowing from America to Europe, departing from America, cool or blue, passing over the ocean, getting heat and becoming warmer or red, and arriving in Europe with much more heat than it had before. And the ocean losing heat, the water gets heavier and sink, and then you have this machine going on and on and on. I'm going to show you one more time. Can you all see what's happening? Oh, the wind blew, getting warmer. And this is something that is happening right now. As we speak, this is happening there. If you go, for instance, to Calgary in Canada and measure the temperature and go along the same latitude to London in Europe, you're going to see a big difference in temperature. From Canada to Europe, the temperature gradient is very high. In the same latitude along, for instance, the northern polar cycle, you have people living in Norway, quite comfortable. On the other hand, on Canada, you're going to find, luckily, some polar bear or some crazy Eskimo. Okay, and my question is, okay, let's see what comes next. There is, or there are some people that says, we human beings, we are not able, we are not capable to cause any harm to the planet. The planet is too big. The planet has a very infinite capacity to recover. So don't worry about global warming. This is a natural phenomenon, and Earth will find a way to recover, and we are safe. Don't worry. And I'm not kidding. You know, there are people that say that. And there are others that even say, greenhouse effect, this does not exist. This is an invention of a conspiracy from, I don't know who, that is trying to scare people, to take people, to have people under control. So, but what is the greenhouse effect? The greenhouse effect is something quite easy to understand. If you lay down during a winter night outside, what happens if the temperature is around, let's say, 18 degrees? I'm talking about São Paulo. This is normally the cool temperature. The wind sometimes gets a little bit cooler. But even 18 degrees Celsius at night, if you are not covered, you're going to feel it. But if you put a blanket over you, you can survive the night quite comfortably. So the physical mechanism happening there is that your body is generating heat, and this heat is being kept on you by the blanket. The blanket is preserving the heat, so you won't get frozen. So if planet Earth didn't have atmospheres, if Earth was not covered by atmosphere, with no water vapor, with no carbon dioxide, with no methane, or other gases that are act like blankets. The heat that we lose to the atmosphere, to the outer space, would be in such a way that the temperature on Earth would be much, much cooler than is today. So we wouldn't survive at night. And this is true. Imagine about the moon. The moon has no atmosphere, and at daytime the temperature is 100 and something degrees. At night time is minus 100 something degrees. So we only survive on Earth because there is this blanket of gases that are transparent to the shortwave radiation coming from the sun and retains the long wave radiation that are sent out from Earth. So greenhouse effect exists, is important. But now what happens if you are quite comfortable with one blanket and then someone brings 2 more blankets and put on you? Even if the temperature is outside 18 degrees Celsius, with 3 blankets, there will be a moment that you are going to sweat or start feeling uncomfortable because you are retaining much more heat than you need. And this is what happened to the planet. We are putting into the atmosphere lots of blankets, lots of CO2 and methane, and removing some vegetation that. So we are interfering. We, as I said before, we are some external factor acting in the climate system. And in short, we are making that the temperature on Earth increases. And what happens if you increase the temperature 1 degree, only 1 degree in average on the planet? There are people that say, oh, 1 degree is nothing. Today I left my house, was 10 degrees, and now it's 20 degrees. The temperature went up 10 degrees in just a few hours. So what should I care about 1 degree? Well, I'm talking about 1 degree in average, in the global average. 1 degree means water that is in the form of ice at marginally 0 degrees. With 1 degree, we will be marginally 1 degree above melting point. So water that would be in solid state would be in liquid state with 1 degree, in lots of water. And what happens with water that melts on, for instance, over Greenland, over the mountains, the Andean or the Alps or whatever? All the water that melts eventually will end up where? Into the ocean. Actually, every water on Earth that evaporates, there's a big chance of getting into the ocean. Or actually, almost certainly will get to the ocean. I don't like to say that, but even if you pee on the floor at the very moment, where is going to be this water sometime from now? In the ocean. Because it will evaporate, be part of the atmosphere, vapor, eventually will precipitate, and eventually evaporate again, eventually precipitate, eventually will end up in the Tietê River, and then eventually into the Paraná River, eventually to the Rio de la Plata, and finally into the ocean. So every water that melts over land eventually gets into the ocean. So if you take 1 degree and calculate how many water will melt and end up into the ocean, you're going to be surprised with how much water will get into the ocean. And this water would increase the volume of the ocean, and the ocean would be with a larger volume with the surface higher. So we would increase the surface elevation of the ocean. And not only that, 1 degree higher the temperature, you have if you ever studied something in terms of thermodynamics, you know that every substance, when warms, they increase in volume. So if you warms up the water 1 degree, you're going to increase the volume of the water as well. So increasing the temperature means that you're going to increase the volume of the water, or the temperature, that means also the volume. So you end up having a surface elevation. But not only that. You're going to interfere as well on the salinity of the ocean. In the north, in the polar, Arctic polar region, there are lots of ice over the ocean. If you increase the temperature, and the water that is melt is fresh water, this fresh water is very light and will remain over the surface of the ocean and spread out along the northern part of the North Atlantic. This will interfere with the density, and the result it would be water that normally comes from south by the Thermohaline circulation will get heavier before arriving in the northern latitudes and sink before getting to where it gets today. And sinking earlier, it won't be able to bring heat to the region where the atmosphere is taking the heat and bringing it to the Europeans. I'm going to show you the animation. Probably the animation is going to be much clearer than what I'm trying to say. And then eventually I come back to the word. But look at this. This is the distribution of ice in the Arctic region in 1984 and in 2016. I'm going to show you an animation again. I ask, please, the lights to be turned off. Please pay attention to what happens surrounding the Arctic region. This is a sequence of winter and summer. The ice forms in the winter and melts in the summer. And again, winter and summer. In the end, you have some water being released around Greenland. As you can see, in the Labrador Sea, you see water coming from this region, you can see this is fresh water. This is fresh water coming to the south. Well, what's the consequence of you having more fresh water being released in this region as a result of global warming? And global warming is, anyone that has some sense of reality cannot deny. So from 1984 to 2016, you see the difference between the distribution of ice in one specific season. So lots of fresh water are around the northern Atlantic since this period. Now, so what? Again, please, lights off. This is going to be similar to the one we saw before. Water coming from the south, warm, wind coming from America, cool, getting warmer, and going to Europe. But then, suddenly, some water, fresh water, start arriving around Greenland and in the Labrador Sea and spreading around the North Atlantic or the Norwegian Sea. And this will interfere with the thermohaline circulation, and in the end, the thermohaline circulation will be interrupted, or at least blocked from the northern latitudes, and you're going to see the consequence. And this is, again, this is not just some sort of delusion. This is serious study. So this is a result of different models trying to understand what would happen if we continue to warm up the planet as we are. Uh-oh. No. Now it's going to. Okay. You see again, water coming from the south, warm, heating the atmosphere. But then, please, look at what's going to happen here and here. There is a kind of light blue color appearing, spreading around. And the wind that comes cool, continuous cool. Because the thermohaline circulation now is changed. And then there is a new glaciation in Europe. So, in short, one likely consequence of global warming is a new ice age in the northern hemisphere. Of course, lots of, I don't believe that. Of course, you have the right not to believe, but then you have to come out with an explanation that is better. Well, that's the point. If you are not in science, if you don't agree with some theory, you have to provide another theory that explains better than the one that you don't accept. And this is a theory. And there are lots of reasons to believe that this is a possible scenario if we continue to warm the planet. So in short, global warming leads to the melting down of the Greenland's and Arctic ice sheets. With the higher volume of fresher water in the North Atlantic, the more saline waters transported from south by the MOC is the meridional overturning circulation, will get denser earlier and sink in lower latitudes. This will result in less heat to warm the westerly winds in the North Atlantic. Then, the temperature will fall down and the new ice age, a new ice sheet will form. This might result in a new ice age in North Atlantic. Actually, when this theory was put forth in the early 2000s, Hollywood made a movie based on that. That's The Day After Tomorrow. And they, of course, the movie was based on a real theory. But the point is, Hollywood is Hollywood. They want to make you guys sit down and watch a movie no more than 2 hours. Otherwise, you get bored. And besides, they want the actor to be there from the beginning to the end. Otherwise, so they had this movie happening in 2 hours of the movie, but in 2 weeks of real time. And this is crazy because this phenomenon, if it happens, is a centurial type of phenomenon. Of course, we already started. We have been already doing this for several decades. Probably, with a few more decades, we can experience some of this, or maybe a century from now. But the point, or the bad news is, the ocean has a long memory. Once you provoke it, it's going to be very difficult to go back to the beginning. And not only that, climate is probably in a kind of an unstable equilibrium state. Once you kind of disturb it, it might go back to an equilibrium, but not necessarily, or very likely not the same one as before. There will be a different equilibrium state. Or in a general statement, we have to get prepared to a new sort of environment in, let's say, 50 years from now. That's why most of the efforts today is not directed to, let's say, mitigation. It's more towards adaptation, because change will happen, and we get to be prepared to survive the new conditions that we will end up in the next decades. Well, we still have 20 minutes, and I want to touch a little bit about modeling. And in the end, I will leave some slides for you guys, but I have to warn, they are in Portuguese, because they are not part of the course. But I added in the end because it's a longer explanation about climate change. And if you understand Portuguese, you can take advantage. If you don't, the slides themselves are quite of self-understanding. But I won't show them in this lecture. I will stop in a few slides from now. Well, what means modeling the ocean? Any physical or biological or any environmental process to be understood need to be observed. I can only build up a good theory if I observe, or even if I have a theoretical kind of theory, I have to do experiments to see if the theory applies in the real world. So observation is the most important component of the knowledge. If you want to build up knowledge, you have to make observations, you have to do experiments. Science without experiment is religion. So you have to do experiments. So you have to understand, if you want to understand the ocean, you have to make observations. The problem is the ocean is very big, deep, and to observe takes lots of time and money and people. And we don't have any country, no country in the world can do observation in the ocean enough for understanding the ocean. There are several efforts going on today, fortunately, that independently of the politics or if it's a communist or capitalist or if it's, it doesn't matter. There are several countries together today trying to understand the ocean. But even so, it's not enough. And because of that, we have to rely on other kind of tools. And modeling is a very important way of helping the understanding. It's not an alternative. It's a kind of, I wrote there, it's a cheaper alternative. It's not an alternative. It's a complement. Maybe the best word that. This is what we call the Global Ocean Observing System. GOOS is an intergovernmental institution that is maintained by almost all countries in the world that are trying to put together an array of observation resources and stations. And this is what we see in the page. I downloaded this in June 2016. So this is very updated. And you can see, you can think that you have enough observation, but that's not true, because each of these points, if you zoom this picture, you're going to see that 2 points are going, the closest ones are at least some hundred of kilometers apart from each other. And this is not enough for understanding what's going in the ocean. And besides, these are sometimes 1 point today, another one 1 month from now, or 1 year from now. So you don't have a good spatial nor temporal coverage. So one way is trying to build up a computer model. It's difficult to explain, but a computer model of the ocean is not something that is made without care. No. Any process in nature, I'm gonna do an experiment. Okay? This has some mass, this has a shape, this has a volume, and I'm going to throw it with some speed in a certain angle, and I'm going to measure the air drag on it, the gravity, if any current of air inside. And then if I have everything, if I know every of these details, I can say exactly where this ball, plastic ball, is going to, after my experiment, I ask you to recover it, otherwise we're going to pollute the atmosphere, or the environment. Okay. Okay? Of course, I couldn't do, I wanted to reach her hand. I couldn't because I didn't do correctly the calculation of the mass, of the form, and besides, it changed the form. I couldn't forecast it. So it's very difficult. But in principle, in theory, I can do it. If I know all the details, if I know exactly the initial conditions, I can make a provision. I can forecast what's going to happen. In nature, in the ocean, it's the same. If I know all the mass of the ocean, if I know all the forcing agents, wind, sun, everything, if I know in detail all the ocean basins, the depth, everything, if I know everything, I can make a set of equations and solve it in a computer. And then I can see the result. Of course I can't, but I can try. And there are lots of efforts being done internationally. I'm going to show another movie for you. This is the last one, I promise. And this movie is going to show you what we have in terms of the more modern or updated effort to understand the ocean circulation in a computer is done by, again, these master conspirators, NASA. Because Earth is not a sphere, it's flat, you know. Okay, please pay attention. This is going to show you the circulation as resulted from a model. And of course, it's going to sometimes speed up, or sometimes slow down. But again, it's very fast because the ocean circulation is quite slow. But I want to be with you the next 10 minutes. So if I follow the real time, we won't leave this room in less than 200 years from now. This is the North Atlantic. The Gulf Stream, you see the Gulf Stream. Lots of rings and eddies or vortices. The ocean circulation is full of little hurricanes. It's like hurricanes or cyclones or anticyclones. The North Brazil Current, the equatorial currents. This is the Agulhas leakage I mentioned. You see those blobs of water that goes from the Indian Ocean to the Atlantic. are going to be from now on. You might ask, is this true? The answer is, well, it's close to the close to the real world. But of course, if you try to go see details, probably there are some details that don't match reality. But that's because we don't have enough knowledge of the present situation to do any sort of real simulation or exact simulation. But in general, this is represents quite nicely what we see in nature. This is the circumpolar current all around Antarctica. And also you can see in this animation the west intensification of the currents. All the currents on the western side of the basin are much more intense than in the eastern side of the basins. The Pacific is so huge that depending on where you see, you don't see any land, you only see water. Okay, so this is an example of what is being done internationally in terms of trying to understand the ocean by means of model. But of course, and now you can turn on the lights, please. But here in São Paulo, we also try to do something. And in collaboration with INPE, we are running a global model as well, with a very high resolution as well, trying to understand specifically the impact of the Agulhas leakage on the South Atlantic and the impacts on the continental the region. There is one of the students came to me saying that he is working on the impacts of the ocean on the precipitation regime on the northeast Brazil. And I told him that I would say a few words about that, and then I will try to do this in the sequence. What you see here is an example that we are running. Please pay attention to this. Waters coming from the Indian Ocean enter into the Atlantic. There are some investigation going on showing that this connection between the Indian Ocean and the Atlantic is changing. There is, in the past 20 years, the Agulhas leakage has been increasing. More water is coming from the Indian Ocean into the Atlantic. And this means the waters in the Atlantic are going to get warmer and saltier than the normal. And what's the consequence of that? Of course, I said that I would show some transparencies in Portuguese. I beg your pardon, I don't want to stay on that. But I'm going to show this, even though the title is in Portuguese, you can understand what you see. Is this water that comes from the Indian Ocean, when mixes with water in the South Atlantic, eventually will flow to the North Atlantic, along the northeast Brazil. And the end of last year, a postdoc of mine published a paper on Journal of Climate showing that there is a very high correlation between changes in the precipitation regime along the Brazilian northeast and the increasing of the Agulhas leakage. Of course, there are still lots of things to do. And for this student from, I think Rio Grande do Norte, he is trying to understand it, and so I advise him to have a look on this. What would be the impact of this increasing in the Agulhas leakage on the drought regime over the Northeast? So this is kind of an important matter to be studied. This is more or less like this. If you have, I would, please, it's important because I wasn't intended to show this, but because of this student, I added, and well, in the end you find a way to understand it. Well, you have anomalies that are entering the Atlantic in this region, and these anomalies, they usually circulate this way. And once they get here in the equatorial region, they would interfere with the exchange of water with the atmosphere. And the wind blows from here to there. So if you have more or less water getting into the atmosphere, eventually this will end up over the continent. And the consequences are, of course, we don't know the consequence, but we are sure that there will be consequences. And this is a hot topic to study if someone is interested, like this young guy from Rio Grande do Norte. And of course, in the end, you're going to have a different water cycle, much more water coming from the ocean in one region, less water going into the ocean from another region, and you change the way precipitation distributes over the continent. And of course, we can't change that, but if we know more or less in advance, we can get prepared. We can move from one place to the other. Like the fish I mentioned in an earlier slide. There are lots of fish in the world ocean that are moving from one place to the other because they don't find themselves comfortable, no longer comfortable in the region they are. Probably going to do the same in our planet. Or maybe even moving from Earth to Mars or other planets. Like there are some crazy guys trying to do this already. So we still have 4 minutes, or 3 minutes according to that. If there is a short question I can answer, or if you can ask more questions, we can stay longer. Thank you. Well, it was a pleasure for me. It has been a long time since I had the full class like the one I saw here. All right, so, there's a question there. Well.
Hello, Prof. Thank you for the presentation. My name is Serge Mayombo from the Democratic Republic of the Congo, but I'm studying in South Africa. I've got a question about, because our research unit is working in the kelp bed forest ecosystem around the Cape Peninsula. So we just found out that our kelp is expanding contrary to what is happening in other regions of the world where kelp are shrinking. So we set some in situ temperature monitoring sites, and we found that there are some events of marine heat waves happening in our region. So it's like we don't understand why the region is experiencing marine heat waves, but kelp is expanding.
Well, I have to say that it's not my expertise. The only thing I can say is that sometimes people ask question, well, if the global, or if Earth is warming, that means that every place, every region are going to experience the sea level rising. So the question is, no, wait a minute. Depends, because in situations like you mentioned, there are other factors. You have not only the ocean rising or going down, but you have also the continental margin that could be going up or down, or some sort of different changes happening. And then when you combine everything, you have a scenario that I can't say much because it's not my field of expertise. But the only thing I can say is that, yes, there are much more to be understood than just what I am trying to understand, or you are trying to understand separately. We have to join forces and try to see what the combination of knowledges could help us to better understand what's happening in the real world. But yeah, I'm sorry, but I can't answer your question because it's far away from my field of knowledge.
Thank you.
Good afternoon, everybody. My name is Krishna. I am from Mauritius. Thank you for your presentation. And we have seen that from your presentation that if we go on increasing the temperature, there might be a possible scenario that the thermohaline circulation might be interrupted, and we may end up with a possible glaciation over Europe. But also from atmospheric models, we have seen that if the temperature goes on rising, it is the European side and the northern hemisphere that is going to suffer the most of the warming. And we are also expecting that in certain cases maybe some 3 to 4 degrees rise in the next century. So won't it be like something contradictory that we're expecting a glaciation and at the same time temperature is going to increase over northern part of Europe?
No, there is no paradox there, because what this possibility says is that if you continue increasing the temperature of the ocean, you can end up with not only 1 or 2, you can even have 3 degrees rise in the global temperature. But the question is, what are the consequences, or what are the consequences, because there might be several consequences of this warming. One possibility is that even if it looks paradoxal, you having a glaciation as a result of an increase in temperature. And this is what happens in a system. When you disturb a system, you can get different answers. And one answer is that, because you are changing the way the ocean exchanges heat. Probably in this situation, you may have a glaciation in North Atlantic, but you're going to have a desertification probably in the Amazon, because other parts of the world other parts are going to be quite different or much warmer than today. And the consequences are to be different. So there's no paradox in that. So this is a possibility. You increase the temperature, and then you disturb the system, and one of the consequences is a glaciation in the North Atlantic, because you are interrupting the machine that brings heat to the north, to the northern region of the Atlantic. And then the question could be, okay, if you don't bring the heat to the North Atlantic, where is this heat going through? It's going to somewhere, probably, and then other regions are going to suffer much more than they should.
Hi,
Yeah.
I'm Amavi from Sri Lanka. So I'm wondering now, this whole weakening of both the oceanic and the atmospheric circulation can lead can impact, can make an effect on, I believe, on the international travel and transportation as well.
For what?
International travel and transportation as well.
Okay.
So my question is, okay, this can again eventually make an impact on the global economy. So my question is, what is your opinion on this, and how do you think is the scientific community as well as the economic community of the world will address this issue?
Wow. Now I'm in trouble. Well, let's like Jack, the how do you call it? The guy in London that used to queue and pick the people apart. So let's go by parts. Jack the Ripper. Well, the answer could be the first one, the easiest one. Okay, this is going to interfere, naturally, because there will be regions where people will suffer more than others. There are regions that might even get better. Because think about, if you live in the north of Canada and the temperature goes up, probably you're going to be much more comfortable there than is today. And then for instance, if you have several acres of land that is under ice now, if it gets warmer, you can I can plant and harvest and get money out of it. So, and then but in the end, most of the people are going to suffer, and then it's going to interfere. But my knowledge stops there. I can't, for instance, I'm not a politician. But one thing I can say, and this is normally I shouldn't say, and especially because it's being recorded, I think. But off the records. We always, when we talk about climate change, when we talk about problem that we are causing to the planet, we never dare to touch about population control, because it's taboo. You see? But yeah, the point is, probably there will be a moment where we have to think in terms of reducing the number of people living on Earth. Or maybe Earth is finding a way to make us ourselves to take some of us out of the business. Because yeah, that's true. If it continues the way it is, it's like a disease. If I have some bacteria on my body, if I don't take care, the bacteria will kill me. And we human beings, we are acting more or less like that. Of course, this is again taboo. But economics has to be taught in terms of this. Every time you talk about the economics, you have to think in terms of what we can produce, what we can, I don't know, there's always an exchange of, and if you have a situation in which the environment is getting much more harsher than it is today, it's going to be much more difficult to make people comfortable. And the economy is going to suffer, certainly. And those who are poor and the weakened part of the rope, those are going to be the ones to suffer more. But again, how to mend that, I don't know. I'm glad I'm a physical oceanographer.
Actually, that was not the question I asked. I wanted you to focus on the travel and transport, maritime transportation and avian transportation. Like, I know that the jet stream, especially, like for an example, weakening of the jet stream can affect the air transportation and yeah.
Okay, no, that's much easier to answer. Of course. No, what happens? We human beings, we can adapt, and that's for sure. Imagine that suddenly you have a current that's going to be stronger in a certain region? Well, of course, if I have a ship that has to go from, well, okay. We remember that I showed the Arctic ice coverage. There are places, there are regions in the Arctic Sea that do not get covered by ice no longer. And then lots of transport business, they are taking advantage of that. They usually had to take the Pacific, go down to Africa, or go to the Panama Channel to get to America, for instance. And now they just go through the Arctic gates. So this is an adaptation. If the jet stream gets stronger and I have to fly, of course I have to fly back somehow. But on one way I would go faster. Okay, this is adaptation. And we are going to adapt. But again, my answer was not that far away from. We have also limit for adaptation. And there will be a moment that we have to find another solution. Like Dan Brown in this Inferno book that was trying to get rid of human beings.
Well, ethical aspects related to the oceans, so it's really important, and this shows us how complex and how interlinked the things are. Yeah? And saying that, I would like to ask a round of applause to Edmo. Thank you very much.